Today's presenters are Herb Schueneman and Jorge Campos. You may remember Herb from the last webinar on writing protocols with ISO 11607 in mind. Jorge Campos is a test engineer 2 here at Westpak and has been with us for 7 years. Herb, take it away.
Thanks, Greg, and welcome to everyone on this Arrhenius Demystified Day. It's always fascinated me, at least for a while, that we put a great deal of reliance in what we refer to commonly as the Arrhenius Equation to calculate accelerated aging for medical devices as dictated by the FDA. However, there's very little understanding, at least in my opinion, of exactly where this presumption comes from. Namely, how in the world do we get from accelerated aging process to a specific amount of aging merely by increasing storage temperature? How accurate is this? How much faith should we put in this, in the results? How in the world did the FDA gain its reliance on accelerated aging based on a formula that talks only about a reaction rate? What are the cautions about using this information? Should humidity be used in accelerated aging? These and a bunch of other head scratchers will be investigated as part of this webinar. And as Greg mentioned, we invite you to submit questions during the process because if you have questions, that means other people might as well. So we encourage your questions. If we don't get to all the questions, we will certainly answer them later if you submit them in the correct fashion that Greg indicated. So with that as an introduction, let's get started. And the place we need to start is this ISO 11607 document. There are two parts of the most recent edition, which is the 2006-4-15 edition. Part 1 is called Requirements for Materials, Sterile Barrier Systems, and Packaging Systems. And that's exactly where we're going to poke our nose for the next hour. This is where we're going to focus our attention here. And specifically, we're going to look at the introduction to this document first. And in there we read that the goal of the document is, among other things, to make sure that product and package systems have the required stability, sterility, and functionality on their expiration date as they did on their initial manufacture, packaging, and sterilization dates. And specifically, 11607 refers to that date as the expiry date. So when they hear that term, that's exactly what they mean, the expiry date. Here's their definition. It's the date by which the product should be used, and it's expressed in month and year. And then there's a validation that they indicate, and this is by examination and provision for objective evidence that these requirements have been fulfilled. So that's the verbiage from 11607, but not all of it. The document treats storage and transit conditions in the same general heading and formats. Notice the document does not define the required storage conditions, only that the storage conditions be defined by the developer of the product. The document also states that the sterile barrier system shall maintain its integrity throughout the life of the period through its expiry date or the point of use, whichever comes first. This would tend to limit the liability of the manufacturer to that exact date. So there's some good and bad about this whole thing. In other words, if the product somehow fails on the day after the expiry date, you're off the hook, so to speak. Notice also that the document tends to lump the product expiration date and the package expiration date together. Some confusion might and often does exist about these two possible separate dates. We'll address that as best we can, but for the purposes of the standard and for this webinar, at least unless the questions are result, we're going to treat those as the same date. So the product and the package system, same date. It's important to note that the standard requires that accelerated aging be validated with real-time aging throughout the lifetime of the product. However, the standard does allow using accelerated aging dates by themselves for claimed expiry dates until data from real-time aging studies are available. And that's important because how in the world are you going to claim that something has an expiry date of 2 years without accelerated aging? That would require that you keep the darn thing on the shelf for 2 years and then start selling it after you verified it was good, in which case you'd need a longer expiry date. So it's required in order to catch up with what's in the future. It's also interesting to note that the standard specifically separates stability testing from performance testing as separate entities. That should be relatively obvious, but it was concluded so that from that I assume that there might have been some misunderstanding about those in the past. Also note that real-time and accelerated aging studies should begin simultaneously. Our assumption is that this requirement goes hand in hand with the acceptance of accelerated aging data prior to the availability of real-time aging data. Okay. Some other preliminary stuff that we have to take care of before we actually dive into Arrhenius is that if expiry dates are based on the performance of the product as opposed to the performance of the package system itself, then accelerated aging study must be conducted on the combination of the product and the package system. You could, I suppose, claim just the package integrity testing and test the package alone, but we rarely see that actually happen. Note that the accelerated aging must be conducted at a number of different, or may be conducted at a number of different temperature conditions based on the response of the materials in the product and package to the effects of temperature. The standard demands a documented rationale for these temperature conditions and durations, and that kind of makes sense if you think about it, because there's going to be components of your product that on some occasions can withstand 60 degrees C, for example, and I bet, and we have seen other components that simply can't do that. Most package system components can because they're designed for that, but there are some product components that just can't handle that higher temperature. More preliminaries from 11607, Section 7 in particular. The document tells us that the expiry date must specifically be stated on the product or package system along with the required storage conditions that might affect it. So if you have a relatively low temperature that the product is sensitive to, that also has to be stamped directly on the product. Use before July 17th, 2018, but keep the temperature below 40 degrees C. So if you have a temperature sensitivity, the standard says it's got to be stated. Appendix B of the standard 11607 also tells us that this ASTM document F 1980 is a suitable guide for conducting accelerated aging studies on sterile medical device packaging. If you're in Europe or selling to Europe, a similar European Union document, which is standard EN 868-8, may also be employed. The two documents are very similar. So when you get done with ISO 11607, it boils down to saying conduct, as far as aging is concerned, that is, conduct real-time aging. That's really what it says. Conduct real-time aging. Validate this with accelerated aging. That's not the other way around. So you conduct real-time aging, you validate it with accelerated aging, and then support claimed expiry dates with accelerated aging until real-time data is available. That's the approach. And I hope that's obvious, but if there's any questions about that, make sure you raise your hand. The test procedure, ASTM 1980 also agrees. It says conduct real-time aging studies and validate accelerated aging with real-time data. That's essentially what it says. Here's an example of how that might look. This table is kind of busy, but let's say, let's pick some actual numbers. Let's say you want a 1-year expiry date, but you want to start selling it as quickly as possible. Well, this says that if your product and package can handle it, age the whole thing at 55 degrees C for a little less than 40 days, 39.7 days, and that equals 1 year of accelerated aging. Okay, and if you can't handle 55 and only 50 degrees C is allowable, then it's going to cost you another 16 days roughly. So you accelerated age it for 56 days, or if it can handle a little higher temperature, then 28 days is correct. So we're going to go ahead now and show you exactly how those numbers are generated, what effect they have, and how in the world they can be derived from what we refer to as the Arrhenius Equation. So I'd like to introduce you now to one, Svante August Arrhenius. Look at the handsome dude we have here. He was born in Sweden in 1859 and died 68 years later, almost the same place, also in Sweden. He studied at Stockholm University and later taught there as well. His field of specialty was physical chemistry. I don't know how many of you have ever taken a physical chemistry class, but I know from my personal experience it was one of the most difficult classes I ever took in my undergraduate days. But for Arrhenius, that was his specialty. Later in his career, he was actually awarded the Nobel Prize for Chemistry in recognition of his advancements in electrolytic theory of dissociation. I'm not quite sure what that is, but it sounds impressive, doesn't it? But that's our buddy Arrhenius. Okay. Before we leave his kind of character, some interesting background that we found out about the man in our research included the fact that genealogy impressed him. He was very interested in the origin of the species and had a keen interest in the ice ages. He was an astronomer. He described himself also as a physical cosmologist. He was active in astrophysics. One of his areas of interest was interstellar collisions. Interesting. He also put forward a complex theory of radiation pressures for accounting for comets and solar corona, aurora borealis, and similar effects. He had very definite theories on the origin of life. Also the possibility of creating a universal language. He proposed a derivation of English as that universal language. He had a very unique theory about the chemical causes of physiological problems. He didn't think there was anything, that there was any such thing as a bad character, just one who had a few chemical imbalances, and that we could fix almost anything with chemistry. He had a very interesting theory of how well the test tube studies simulate real life conditions, and he was able to prove that. Most interesting to me, I thought, was the fact that he had a very high interest in carbon dioxide, the burning of fossil fuels, essentially, and its effect on global warming. Ever heard that before? And the greenhouse effect. So the man was definitely ahead of his time, and certainly in some of his interest areas. So that is Svante Arrhenius. So when you hear his name again, you'll know a little bit of his background. Here's the equation for which he's famous, or at least we think he's famous. We call it the heart of the Arrhenius, and it's a relatively simple correlation between the rate of a chemical reaction and its absolute temperature plus the activation energy of the reaction. We're going to talk about that in a minute. The universal gas constant, I remember that from my chemistry days, but I couldn't pull it out of the air otherwise, and a prefactor. which is not yet fully defined, but we're going to tackle it here. That's the A factor in this equation right here. Okay. Most simply, in the Arrhenius equation, K is the number of collisions that result in a reaction per second. A, this prefactor, is the number of collisions per second, okay, whether or not they lead to a reaction. And then this factor E to the power of minus activation energy divided by the gas constant times the temperature, Kelvin, is the probability that any given collision will result in a reaction. Kind of interesting. Well, you can see that that this equation is based on temperature, and that increasing the temperature or decreasing the activation energy, for example, by means of a catalyst, will result in an increased rate of reaction. So here's the Arrhenius equation. It doesn't look anything like accelerated aging, does it? Well, it sure didn't to me, at least not in first exposure. So Jorge is going to explain that now, but before he does, I want to delve into this thing called the activation energy, this E sub A. And activation energy is shown in this graphic representation where you see there's a hump which molecules over which they must travel in order to combine in an energy state. Okay, so here's your reactants. Okay, so they have to have some energy input in order to get over the hump so that they result in products of the reaction with a lower energy state than the reactants. Okay, that's the theory of this activation energy. It plays an important part in the Arrhenius equation and the derivation of accelerated aging from that equation. And Jorge will now attempt to fill in the gaps between what I show as the Arrhenius equation and what we currently define as the accelerated aging factor. So Jorge, want to take it away?
Thank you, Herb. The question is, how do we go from the first order Arrhenius equation to the accelerated aging factor equation? Well, let's first think about what we want to accomplish here and do as follows. Our intent is to determine the relationship between the reaction rate and temperature for the same material or solution. We're going to solve for the activation energy through algebraic means, but first we're going to write two Arrhenius equations with different reaction rates and different temperatures. We will then equate both formulas to solve for the activation energy. Let's remember that since the same substance or material, the number of collisions A and the activation energy E sub A must be the same for both equations.
Pardon me, I'm going to put some comments in here because I'm a little bit slower than what Jorge is. What we have essentially done is we've created two separate rate equations, okay, and we're calling them K1 and K2. Okay, they both have the same A factor. They both have the E to the activation energy power divided by the gas constant times some temperature, T1 in the case of K1, T2 in the case of K2. So basically all we've done is set up two separate rates, and we haven't really defined the differences between them yet. But that's our starting position. Jorge?
Let's take the natural logs of both sides with the purpose of solving for the activation energy. Using the natural log product rule, let's break the natural log of A and separate it from the exponential function portion of the equation.
Okay, again, what have we done here? We've simply multiplied both sides of both rate equations by the natural log. Okay, so we've taken the same equations we had on the previous slide and we've multiplied them by the natural log in both cases. So we haven't changed the equation, we just added the log in. Okay. Then what we do then is use this natural log product rule. So what's the product rule? Well, as I remember it from my I think, high school days, working in natural log, the products are always 2 steps behind. So if you have the multiplication in these top logarithmic equations, okay, 2 steps behind multiplication is addition. So what you have is the log of K1 equal to the log of A plus the log of e to that power, and the same thing with K2. Whereas before you had the log of the multiplication of that factor times e to the activation energy factor. So all we've done is apply the natural log product rule. Okay, so it looks complicated, but that's exactly what happens. And I've been I know that it works because it worked a long time ago and it still does. So okay, Jorge, let's go back to you.
Okay, so let's now cancel through the natural log from the Euler's number, which in this case is e sub a. I'm sorry, e sub x, and finally arrange both equations to equal to the natural log of a.
Okay, so what have we done here? We've taken this natural log rule, the log of e to the x is equal to x. So we've basically taken the equation of the a to the power of e to the a over RT1 and RT2 on each side of the equation, okay, and we replace them with x because the Euler's equation says that we can do that. Euler's number, basically, okay. So we have log of K1 equal to log a minus e sub a over RT1 in the first equation, and log of rate 2, K2, equal to log a, again the same thing, minus the activation energy over the gas constant times T2. Okay. Well, you can see that there is a log a in both equations. Okay. So what Jorge did in the second set of equations, he simply factored those out in both cases. Jorge, you want to continue?
Since both equations now equal to the natural log of a, we can then set them equal to one another. With some additional rearrangement, we can then set the natural logs of the reaction rates on one side.
Okay, this is Herb sticking in again. So basically all we've done in the top equation is that we've made log a equal to log a in both cases, except we're defining it in terms of what it's equal to in both equations. So now we have a single equation that has log k sub 1 with temperature 1 on the left side, and log of the second rate equation plus e sub a divided by r temperature 2 on the right-hand side. So far we know that those are equal. So now what we're going to do is to rearrange those so that we have log K2 minus log K1. So basically all we've done there is that we have subtracted log K1 from both sides. Okay, and that's the equation we get at the bottom of that particular slide, number 22. Okay, I hope everyone's still with us. Jorge, you want to continue?
Using the natural log quotient rule, we can then divide K2 by K1, which is no longer a reaction rate, but a ratio of 2 reaction rates, and it is unitless. In other words, the ratio of reaction rates becomes a function of the activation energy when temperature remains constant at 2 set points.
Okay, once again, what we've done here is simply divide both sides by the log of K2 over K1, I think, is that right? Yes, okay. And use what he called the quotient rule. And the quotient rule basically says, again, that the logs are 2 steps behind, and since they were division before, now they become subtraction. So we have the log of the rate, K2 over K1, which, as he pointed out, is unitless, okay, equal to activation energy divided by the gas constant at temperature 1 minus activation energy time divided by the gas rate times temperature 2. Okay. Now that's you have to work on that one a little bit, but it does actually work, and I've done that, so I can, unless I screwed up, I can see where that works. In the lower equation, what he's done is to simply factor out this factor of 1 over temperature 1 minus 1 over temperature 2. So you can see that's a relatively straightforward algebraic equation. So we're getting pretty close. I hope everyone's still with us. Jorge, can you take us to the home base here?
Since we now understand the relationship between reaction rates and temperature of a homogeneous process, let's see what happens when the reaction rate doubles by dividing K2 over K1. That means that if we divide 2 by 1 is 2, and at ambient conditions of 295 degrees Kelvin and 305 degrees Kelvin, which is between 22 degrees Celsius and 32 degrees Celsius respectively, has a change of temperature of 10 degrees. The ideal gas constant R is a constant and remains the same value for any given equation. Once we solve for the activation energy, we get a value of approximately 50 kilojoules per mole.
Okay, this is the important step here. So now that we have the relationship between the rates of two separate equations, K2 divided by K1 in our particular case, and so we can define that in terms of a doubling, so which means K2 is twice K1. So that's exactly what we did in that equation. And then we can also take the temperature and say, okay, we're going to find out what's going on from an activation energy standpoint if not only we double the rate, but also increase the temperature by 10 degrees Kelvin, which is the same as 10 degrees Celsius in this case, because the gas constant R is in fact constant, 8.314 joules per 1,000 moles. And as Jorge pointed out here, that results in a equation of E sub A, the activation energy, remember that was the hump we got to get over, equal to 51.85 joules per mole, or what we approximate as 50 kilojoules per mole. That's the key thing, so I hope everyone followed us there. Jorge, can you finish this up?
Again, the ratio of reaction rates doubles when the activation energy is 50 kilojoules per mole, and at the difference of temperature of 10 degrees Celsius. The temperature of interest to us are ambient conditions, and if we express it graphically, the ratio of reaction rates increases as the activation energy increases. In this chart, we can appreciate what the increase of activation energy does to the ratio of reaction rates while maintaining ambient conditions. For our purpose of interest, we can see that at 50 kilojoules per mole, the ratio of reaction rates doubles at ambient conditions with temperatures of 10-degree difference. This plot shows the relationship of temperature and the ratio of reaction rates. If we were to change the ratio of reaction rates to be a function of temperature and kept the activation energy constant at 50 kilojoules per mole, we can then see that the ratio of reaction rates decreases as temperature increases. Here we can see that the temperature range of 20 degrees to 70 degrees Celsius causes the ratio of reaction to be approximately double across the temperature range. So from all this, how do we determine the accelerated aging factor formula? From the Arrhenius equation, we now know the following. The ratio of reaction rates doubles in our terms. It really represents Q sub 10 equal to 2, with a temperature change of 10 degrees and an activation energy of 50 kilojoules per mole. Now Herb is going to explain how to use this in the aging formula. Herb?
Thanks, Jorge. Now we know from Jorge's equations that the accelerated aging formula given in ASTM F1980 is in fact derived from the Arrhenius rate equation. So we can turn our attention to the standard exercise about the use of the formula. And what it says is that aging is a chemical reaction that involves the deterioration of materials in a homogeneous process. In addition, validating the accelerated aging with real-time aging requires determining this Q sub 10 value for a 10 degrees C temperature change. By the way, I would like to mention for our audience that these equations can be somewhat daunting on first exposure. They certainly were for me. So what I'd encourage you to do is to study them at your leisure in a format that is relaxing for you, and see if you can work them through. They're relatively straightforward. There are some precursors such as the quotient rule and Euler's ruler and that kind of stuff, and we can certainly help you with those. But I would encourage everyone to sit down in a quiet place when they have some time to reflect on it and look at these. The slide stack will be available on our website shortly after this presentation. How long is shortly? I really don't know, but within a day or two or three or four, enough time so that when you're ready to tackle it, you can probably get it. But I would encourage you to let it simmer for a while before you actually go back to it, so that you're able to follow the systems through. Okay. It's interesting to note that while the ASTM F 1980 standard defines this deterioration of materials that I mentioned earlier, that follows the Arrhenius reaction rate function. This so-called deterioration of materials is never mentioned in the original Arrhenius equation. It's never there. I thought that was kind of interesting. It's also interesting and informative to note that the ASTM F 1980 standard refers to a homogeneous process, right from the standard. Other authors have confirmed that this homogeneous process is another way to define the activation energy of about 50 kilojoules per mole. Okay, so when you see the term homogeneous process, basically that's what it means. And our observation on this slide is that this homogeneous process comes from solving for a rate differential, K2 over K1, when the difference between the aging temperature and the room temperature is 10 degrees C for a slow rate or homogeneous process. So those three have to be together. The rate differential, K2 over K1, the temperature differential, 10 degrees C, and homogeneous process, which basically means how fast is this reaction rate. Okay. So those are the key factors. Okay. So what exactly is this slow rate or homogeneous process? We found a very interesting source, and I think it's actually referenced in the ASTM F 1980 document. And basically what it says, it gives three separate curves for different reaction rates. It gives this top A curve here for a reaction rate of 100 kilojoules per mole. It gives the second, or the B curve, for the reaction rate of 75 kilojoules per mole, and the lowest one, the C curve, for a reaction rate of 50 kilojoules per mole. Well, if you take the 50, which we're using as our baseline because it is a slow rate process, okay, we can see that in the temperature range that we're interested in, which is about room temperature, here about 310 degrees Kelvin, which is very close to room temperature. So we notice that this rate has a value of 2 for temperatures at or near room temperature, about 305 degrees Kelvin. So that is an independent confirmation of this Q10 value that Jorge mentioned earlier of 2. And the source of this is this J.E. House. He wrote a Principles of Chemical Kinetics in the early 1970s, actually, and he was employed at the Department of Chemical Engineering at the University of Illinois. Good document if you have time to read it. Now, finally, we have the basis for this accelerated aging based on Arrhenius. Okay, and it's exactly this accelerated aging factor equals Q sub 10 to the power T sub AA, in other words, your accelerated aging temperature, minus the room temperature, so that's the difference, divided by 10. Okay, so this is the easiest form of the accelerated aging factor equation, and all the variables are listed right there, the Q10, the temperature, accelerated aging, and the temperature real-time aging. I'd like to point out that in our earlier webinar, someone asked the question, is that T sub AA talking about temperature or time? And clearly we're talking about temperature here, temperature only. Okay, so temperature of the accelerated aging and temperature of the real-time aging. Okay, C. So that defines our accelerated aging factor. By itself, it's not much use to us because we're interested in time, not a factor. Well, the equation at the bottom tells us that in order to get a certain accelerated aging time, which is really what we're looking for, this T sub AA, all we have to do is take our desired real-time data, and let's call it a year, and divide it by this accelerated aging factor. Then we got it, and we know exactly how long we need to put something in a certain temperature in order to get the equivalent accelerated aging that we're looking for. So let's take a look at how that's done. I've selected 10 steps by which this process is actually used in what I'm going to call the real world, or how we actually do it when we go to about aging medical devices. First of all, we select the Q10 value. Okay, now how in the world do you do that? Almost everyone that I'm aware of anyway will select a value of 2 initially until you can prove otherwise. And it actually is a pretty good value. Most of our clients use a value of 2 unless they've done specific studies to prove otherwise. And even if they do, it winds up being very small difference from a Q10 equal to 2. Next, you design or define the desired shelf life, and that might come from marketing needs, it might come from Lord knows what, but you have to define how long you want to be able to age this product for and package system. You define your aging test time intervals, including the 0 time intervals. And what does that mean? Well, remember, you have to validate accelerated aging with real time. So are you going to do that every 30 days, every 90 days, every 180 days, or every year? So that's what we refer to as the aging test time intervals. And that's up to you. Then you define your test conditions, your room temperature and your accelerated aging temperature. Now, room temperature is interesting because some people say, well, it must be 21 degrees C. No, I like to be a little bit warmer, etc. ASTM F 1980 says use a temperature between 20 and 25 degrees C. So almost always you find those temperatures used. And then you also have to define your accelerated aging temperature. Kind of tricky in some regards because you have to have a temperature below certainly the glass transition temperature of some of the polymetric materials that you're using. So make sure that you're not raising the temperature so high that you actually start melting some of the polymers. Also decide if humidity will be used in the aging process. Now we're going to talk more about humidity a little bit later, but that the standards, for example, 11607 says you have to consider humidity. We'll talk about that in a minute. Step 6, calculate the test durations based on the accelerated aging factor that we talked about a minute ago. And then you have to define the sterile barrier properties. In other words, what are going to be the acceptance criteria? Some of them might be peel strength of the pouch materials, or a number of other things, but you have to define those ahead of time. Then you age your samples at your accelerated temperature, and in parallel, you start your real-time aging test, T sub RT. You evaluate the sterile barrier performance after the aging, accelerated aging, and the initial sterile barrier requirements. For example, like I said, seal strength, package integrity, a number of different requirements. Those are up to for you to determine again. And then evaluate the sterile barrier system after the real-time aging relative to their initial design requirements, and then you compare the real-time to the accelerated. And if those coincide, you're home free. Okay? Sounds complex, but actually works out fairly well. Some cautions and notes are added in the ASTM F 1980 document. These include the fact that aging studies and performance testings are separate entities. Well, of course they are. Who wouldn't think otherwise? Well, apparently someone did, or some people did, which is why it's specifically stated in this document. So even though it's obvious to the casual observer, it's likely that some confusion existed early on, requiring that the writers of the standard include a note like that. It's also interesting to note that the standard requires establishing acceptance criteria prior to conducting the aging test. Once aging results are obtained, they should be compared to the zero-time performance data for the package. However, another trend, another possibility or a trend that we see is allowed by the standard, and that's to incorporate trended data over all periods. For example, let's say that you test over a 30-day increment, 60-day, 90-day, etc. And instead of using the zero-time data, you use the trended data over all those periods. It's allowed by the standard, and some people think it's a little more conservative. I'm not sure. Finally, the standard cautions to use the final test period results for evaluation purposes. What does that mean? It means the unknown. You use the latest period results. For example, if you're validating a 2-year accelerated aging with a 2-year real-time aging, you actually use the data that you just got out of your 2-year accelerated aging, which is the latest data for your comparison. Okay, same thing with the real-time data. Okay, a little dry here, but we're moving right along. One of the questions that we're often asked regarding the sequence of aging and package performance testing is which one comes first? In other words, should you do package performance before aging or after? In most cases that I'm familiar with, the aging would be done after package performance because most people consider that the product would likely be shipped from the manufacturer to the customer and then stored at the customer's location. And if this is the case, it would make sense to conduct aging studies after package performance. The reality is, however, that the package performance testing may be conducted after aging, which would indicate storage of the product would occur at the manufacturer's location or some other location other than the customer's. It turns out that either way is acceptable. Acceptance criteria should be based on the package performance data conducted at the beginning of the aging studies, whether or not that involves most package performance testing. So it really doesn't matter either way. Your acceptance criteria may change, but you can do your aging before or after the actual package performance testing. I thought that was mighty good of them folks. Finally, the bottom line is the conformance with the accelerated aging and the package performance testing outlined in 11607 provides proof that the packaging system will allow for sterilization and guaranteed product functionality up to the point of use. And that was, if you remember, that was the whole criteria of 11607. Thou shalt basically make sure that it's good no matter where it is up until the time that the expiry date is still in effect. There's an interesting component of this ISO 11607 in that it mentions a consensus standard. What is a consensus standard anyway? Well, it might be good to review that since we have a little bit of time. A consensus standard is one that is requires everyone to agree on it up to the point where they are persuasive in their arguments. I'll give you an example. ASTM is a group of volunteers, basically. There's a paid staff, but it's mostly volunteers. And they get together twice a year, and they sit around the table, and they discuss topics regarding standards that they have an interest in. And that interest has to be balanced amongst the people around the table. So there has to be some people that represent the view of a manufacturer, some people that represent the view of an end user, and some people that represent what they call a general interest view. And that the committee has to be balanced. In other words, you can't have it skewed toward manufacturer or consumer or none of the above. In addition, when they agree on a standard, everyone has to agree. And if someone doesn't agree, then they're free to write a position paper. And if it's considered to be persuasive by the group, then the standard has to change in order to accommodate that view. So that's a consensus standard in essence, as opposed to other standards where a group of people that are either appointed or volunteer for a committee write a standard and say, here it is, it's the best job we can. So it's not consensus. Many of you likely are aware of the fact that for performance testing, standards such as ASTM D4169 are often used primarily because they are consensus standards. 7386, D7386 is another one that's often used. So these are consensus standards because they come out of a consensus standards organization, ASTM. We've often been asked, well, what about ISTA, International Safe Transit Association standards? And it turns out that up until recently, they were, in fact, not consensus standards. But we've been informed that the steps are underway to make them consensus standards based on approval from ANSI, which stands for American National Standards Institute. Now, it hasn't been officially announced or accepted yet, but we understand it is underway. So hopefully in the future we'll have the ability to expand the amount of test procedures that we have available for our clients based on the consensus standards rating of ISTA, and hopefully that will come about fairly soon. Okay, let's move along. By this time I hope everyone has seen that accelerated aging is part of the standard, part of ISO 11607, and that it does trace its origin to the Arrhenius reaction rate for this accelerated aging of medical device. In particular, however, there are those who think that it may work for some materials and not others. So it's not what I refer to as a universally accepted ism. It should also be noted that the Arrhenius equation extrapolated beyond very cold temperatures, which is really where it started, may result in a non-linear condition not anticipated by regulatory bodies. The reason we mention this is that it's not clear that it is clear that not everyone agrees that Arrhenius extrapolations, as they're called, result in a true accelerated aging condition. In particular, we would draw your attention to this particular source, and I believe it's referenced in one of the standards that talk about this. This is by Weiss, Gillen, and Clough, fairly recent paper, and it's entitled "An Ultra-Sensitive Technique for Testing the Arrhenius Extrapolation Assumption for Terminally thermally aged elastomers. Okay, well, that sounds like it's right up our clock. So if you're interested in this and want to hear their reaction to it, I would highly recommend that paper. Another question that we're often asked, and one that is a source of much confusion, is how about humidity? Okay, well, let's tackle this one, shall we? Humidity is mentioned in the ISO document 11607, but look here, it only mentioned it as item 5.1.4, as a minimum the following shall be considered. Okay, temperature, pressure, and oh, look at this, humidity. So what 11607 says about humidity is consider it, just like you would rate of change, maximum rate of change, exposure to UV, cleanliness, bioburden, electrostatic conductivity, lots of different things. So consider it. It doesn't say do it. It says consider it. Okay? I thought that was an interesting way to handle it. ASTM F1980 gets a little more specific. Look at this. It says that the accelerated aging time, in this case they do use a time TAA, is not applicable for, the humidity is not applicable for accelerated aging protocols. That's interesting. It says that unrealistic or extreme temperature conditions may be of interest, but this must be evaluated on a separate study and is not related to the aging of materials. And it's interesting. So F1980 says, nope, don't use it. But it goes on to say, decide if humidity conditions will be used in the aging study. So it doesn't exclude them. And so it says, if used, define these conditions and the allowable tolerances. Interesting. They're not big on humidity. You can tell that right off the bat. Here's some observations that we'll offer for your use. Number one, can I use humidity in accelerated aging tests? Certainly. Understand, however, that it just adds complexity without a clearly defined benefit. That's probably the most definitive statement that I've heard anyone make about humidity in accelerated aging. As I mentioned earlier, ISO 11607 mentions humidity only in passing. Arrhenius doesn't mention it at all. The Arrhenius equation talks about temperature only, no humidity. So the question is, when is humidity important? Good question. Perhaps it's important when dealing with hydroscopic materials, in other words, those that absorb moisture. But we recommend evaluating this on a case-by-case basis, not by applying it universally without careful examination. Also, we should point out that the psychometric chart, most of you are familiar with the psychometric chart, clearly tells us that the activation energy of moist air is greater than dry air. In other words, air at, pick a number, 50 degrees C, at low humidity has a lower activation energy than air at 50 degrees C and 50% relative humidity. So there is something to it. It's just not clearly defined, and the value of using it is not clearly understood as well. Yet another mystery in our life. Okay, at the risk of getting kind of bogged down here, let me go through some conclusions, and then we'll see if any questions remain. So at the end of this hour-long dissertation, I hope that we have shown definitively the following three items. One, that the accelerated aging formulation in this ISO 11607 does have its basis in the Arrhenius reaction rate equation. I hope we've shown you that there is a relationship between the two. Secondly, I hope we've said that not everyone agrees that accelerated aging formulation is valid for all materials and all temperatures. That I think is pretty clear. Not everyone agrees that that's a good way to do things. Finally, that accelerated aging validated with real-time aging is the best approach for complying with the ISO 11607 requirement of stability testing that demonstrates a sterile barrier system that maintains integrity over time. So that the underline over time, that's the important thing. Okay, that's what we're really trying to do, and that's what the accelerated and real-time aging does for us. Okay, so I hope it's not been as dry as sawdust. I realize the topic is not just full of dancing and all that kind of stuff, but I hope you have a better understanding of it and that you're able to better defend it the next time someone pins you against the wall and say, what in the world are we doing this for? Greg, are there any questions that have shown up from our audience?
Yeah, we have a few here, Herb. The first one would be, would it ever be justified to conduct real-time aging for non-sterile materials such as product labeling? To not conduct. Can you skip aging for non-sterile products for labeling and such like that?
Let's see if I can understand the question. Does it apply to non-sterile products? And the answer is yes. There is no requirement in the Arrhenius equation or in the derivation of it in ISO 11607 or ASTM F 1980 that would say that anything reacts differently whether sterilized or not sterilized. Okay, so sterilization has no effect on the aging rate at all. Okay, any other questions, Greg?
Another question, what are the common aging temperature ranges that you would see for accelerated aging?
Good question. The vast majority of the aging conducted by Westpak is at 55 degrees C. It appears to be kind of a sweet spot in the range of testing temperatures that provides sufficient time contraction, if you will, in other words, accelerated time, accelerated aging processes, without causing degradation to the materials excessively. Having said that, there are clear cases where this is way too high a temperature, and there are some cases where you're kind of snoozing along and you could go at a faster rate. However, when we look at the volumes that we have at various temperatures, most of them are at 55 degrees centigrade. Greg?
Cool. It looks like the questions that we have left here are a little bit long for the time we've got left in the webinar, so I think I'm going to go ahead and wrap things up unless you guys had other comments you wanted to add in.
I should mention that there was a question at the morning webinar session that had to do with the effect of pressure on the accelerated aging process, and the answer to that is there is no effect unless something is very compressible at very minor pressure changes, and I'm not aware of anything at all. Neither ISO 11607 nor any of the other documents that I mentioned, especially ASTM F 1980, have any mention of pressure, either atmospheric pressure or absolute pressure. Okay. Jorge, do you have anything to add to us?
Not at this moment, Herb. Thank you.
Cool. Well, Jorge and Herb, thank you for the presentation. If you missed anything or would like to listen to the webinar again, please check Westpak's website at www.westpak.com under the Events tab. The webinar should be uploaded shortly. All the people that are registered will receive the email within 5 days with a copy of the recording and a link to download the slides. Check our website for upcoming events for our next webinar. If you have any questions, please send them to projects@westpak.com. If there are any other webinars you'd like to see us offer, please also submit them to projects@westpak.com. We will be sending out a short survey following the webinar. Please fill it out, as we are always looking to improve our process. Thank you for attending. I'm Greg Swinghammer. Make it a great day.